Okay, so for homework 7, I basically just worked through some of the problems, and so hopefully this will be satisfactory for the purposes of like understanding the solutions, which is what section is normally supposed to be for anyways. So the first problem here is about price discrimination, and in this case, you can just set them up as like separate profit maximization problems, and you can solve each of them separately and just add them together to get the solution that you want. And so here what you have, right, is that you have a profit condition for the entirety, which is basically your standard kind of there's revenue there, and then you subtract out the costs, and then we're looking at first for an interior solution, and so we require that both of the partial derivatives are 0, and that'll give you straightforwardly the answer. I mean, this is effectively like solving two profit maximization problems via one equation, I guess is one way you can think of it if that's helpful. And so you'll get these answers, and I kind of omitted to do the calculations for the rest of it, but it's pretty straightforward, right? Because you can just take these quantities here and you can plug them into these price equations up here to get the prices and to the profit equation for the profits. So that's 1A. And 1B asks us to consider the case where there's no price discrimination. And then the trick is we basically need to take the two separate demand functions we were given and turn them into an aggregate demand function. And there's a little bit of a complication with that, as we'll see, because demand is only ever non-negative. And so you can't just add them together because in some cases, so for example here, right, if the price you set is greater than 100, then what you'll get is a negative demand, which shouldn't happen. So the way we deal with this basically, and the way we deal with this basically is to consider when each of the separate demands is going to go to 0, and then we do it by cases to handle those cutoffs. So what you'll ultimately get is that, oh, I'm on the train, so if there's any background noise, my apologies. So what you'll ultimately get is a piecewise function for the demand as a function of price that looks like this, and if it's helpful, you can plot it to see the question talks about like a kink in the graph, and if you plot it, what you'll see is that there's a point at which the slope changes instantaneously, and so using this function or this graph, whichever helps you more, you can get this price function, which is the price that fits that quantity demanded. And then what we basically want to do is solve the standard monopolist problem by setting the marginal cost equal to the marginal revenue. And it's easy to tell from the structure of the cost function, right, that the marginal cost is just going to be 1, because for every unit you're producing, it is going to add 1 here. So marginal cost is 1, and then we just try for these different sections of the graph the relevant marginal revenue. And so in the case where x is less than or equal to 70, you know, we check that we're in this case, and so we can use this stuff. And what you ultimately get is that after setting it equal to 1, you'll get that the x is 49.5. And then you consider the case where x is greater than 70. You have the revenue equation, marginal revenue, and you get that x, the optimal x, will be less than 70, which is a contradiction, and so you know that your previous solution is the right one. So now we're asked about perfect competition, which is something we know a lot about. Basically, the price is always going to be the minimum of the average cost, and so it's straightforward to compute what the minimum of the average cost is going to be by taking the first derivative and setting it equal to 0. And so if you do that, what you'll get is that the ideal amount to produce is 50, and the cost there is going to be, the average cost there is going to be 42. The second part asks about the monopolistic competition case, and what we're going to do in this case is solve a system of two equations. So the first equation we want to solve is an analog of the standard monopolist case, right, that marginal revenue equals marginal cost. But also, because there are all these other firms in the market, what we need to ensure is that the price is equal to the average cost there. Actually, scratch that last part I said about there being other firms. Truth be told, I'm not entirely sure, or I haven't checked why these are the relevant two equations, but I trust that in lecture you guys were given some intuitive explanation of why this is the case. So anyway, the computation is straightforward as always, and so we can find the revenue, and then we can find the marginal revenue, and we can set them equal, and I've omitted a bunch of the intermediate algebra, but hope to be forgiven for that. And so you can solve out this system of equations, and there are two equations, there are two unknowns, and so unless they're weird dependencies that we don't see, that don't look to be the case, you can solve out for y, I, and n, and then plugging those back into the function you were given, you can get p. Okay, so that's 2b. And for 3, so 3 is a Cournot equilibrium problem, and the first thing to do in 3a is to find the best response functions. The way you find the best response function is you just suppose the other firm is producing some quantity, so suppose h2 is some fixed number, and then you do the standard profit maximization problem for h1. So if we suppose h1 is, I did it the other one first, so if you suppose h1 is fixed, you ask what would be the best h2. You have this equation, which is our standard price times quantity for the revenue minus our costs. Now we maximize, and again we take the first derivative and set it equal to 0, and we get this function. Important that it's going to be a function because it's going to depend, of course, on the value of h1. Now we do exactly the same thing, but the other way around. So we fix h2 and we ask what would be the profit maximizing h1, and we'll get this function. And the solution to a Cournot equilibrium problem is going to be any points where both this function and this function are true. In other words, it's any solution to this system of equations. And of course, we can just solve out. Again, I've omitted some of the algebra, but this should be doable. And so what you'll get is these quantities for h1 and h2, which then, going back, you can substitute into the relevant equations in order to get what the prices will be and what the profits of the respective firms will be. Part B asks us to consider the case of collusion. So when they collude, you're going to basically treat the two firms as one firm with like a unified profit function, and then you're going to solve for the optimum for that firm. So what we'll get then is that this is going to be the price as a function of h1 and h2. This is, of course, going to be the quantity of h1 and h2 they produce, and we subtract out the costs. And then since we can control both h1 and h2 in this case, we require that both partial derivatives are equal to 0. And of course, there's some more algebra here, but eventually you'll get this system of equations, which you can immediately see has no solution, because if it had a solution, we would get that 400 equals 30, which is not supposed to be the case. And so there can't be any interior solution. Now, the reason why we can only conclude that there's no interior solution and not that there's no solution generally is because when we require the partial derivatives to be equal to 0, we're basically saying that we're only looking for an interior solution. If there's an interior, because the intuition, right, for why the partial derivatives have to be 0 is that if it's an interior solution and it's not 0, then you can always move slightly in some direction. So suppose it's negative, then you can move slightly in the other direction in order to increase your profit. And if it's positive, you can move slightly in the positive direction, increasing h1 in order to increase your profit. And so these conditions basically reflect the thought that we're looking for an interior solution, but now that we know there's no such solution, we get to check for exterior or boundary solutions, and those are basically solutions of the form h1 equals 0 or h2 equals 0. Now, here's some intuition for the right answer. If you look at the cost function, you can see that the cost for firm 2 producing anything is just greater than the cost of firm 1 producing anything. And if you look at this profit function, they kind of both get treated the same, quote unquote, in the revenue part. So you might think that, well, if there's going to be a boundary solution, it's got to be one where firm 2 is not producing anything because they're just costlier producers. The way to actually show this is to check each case explicitly. So we set h1 equal to 0, and we do the profit maximization thing, and we get that the profit is 4,500. Now we suppose that h2 equals 0, we do the profit maximization thing, and we get 8,000. Of course, 8,000 is greater than 4,500, and so that's going to be the outcome. And the problem also stipulates that there's a 2/3, 1/3 split, and so that's going to be how much they get. And of course, from this, from h1 and h2, you can calculate. Oh, actually, that is everything that we needed to solve for. Oh, and you can calculate the market price, of course, from h1 and h2, because you have the price function as a function of h, which is just their sum. So now we ask, whether any of the families have an incentive to break the agreement, and so what it means to break the agreement, I guess, is that you suppose the other person is going to do their part, produce, that is, the agreed upon quantity, and you wonder, can I get any extra? And of course, Corleone can get something extra because Corleone can decide that they're just going to keep all of the 8,000 instead of giving a third of it to Chung. And so there's going to be a clear incentive on that side to break the agreement. The question is more interesting from the other point of view. So suppose Corleone is going to uphold the agreement, that is, give 8,000 over 3 to Chung at the end of the market period, and that h1 is going to be equal to 400. Now we ask, does Chung have any incentive to defect? And so what we check basically is, in the case where h1 is 400, is there any value of h2 that would result in Chung getting more than 8,000 over 3? And this is like our standard profit maximization problem. We just plug in 400 and try to find a relevant value of h2. And so we get that this is our profit function. And now we take the first order derivative, and we set it equal to 0. And at the end of all that, what you get is that h2 has to be 100. And you can calculate then what the profit will be in that case, and then you're going to get 500, which is a lot less than 8,000 over 3, so of course he has no incentive to defect, or she has no incentive to defect in any case. So for 4-star, I guess I should pause. If you want to pause and try to draw out the game tree or anything like that. So the diagram, though, just looks like this. And so, you have the players at the nodes, and then you have the actions that they can take, and then you have the payoffs at the end of the game, where the first one, of course, is always player 1's payoff, and the second coordinate is player 2's payoff. And now the question asks, find the backward induction solution. So the way we find a backward induction solution is we say, basically, look at the last stage of the game. So that's these two stages. And we ask, what will player 2 do here? Well, of course, player 2 is going to pick L because 1 is better than -1. And here, of course, player 2 is going to pick H because 3 is better than 2. So now, if player 1 picks H, then we get L. And if player 1 picks L, then we get H. And so now player 1 knows this, and so player 1 considers, well, which case do I prefer? So if we do H and L, player 1 gets 3. If we do L and H, player 1 gets 1, and so 3 is better than 1, and so HL is going to be the backwards induction solution to this tree. Now we ask, should firm 1 listen to the following threat? I'm always going to produce H because I'm a tough guy. And I guess the idea, right, is, so if you really think that player 2 is always going to produce H, then of course player 1 should pick L, because 1 is better than -1. But they shouldn't really listen to this threat, because the payoffs clearly show that that's not going to be in their rational interest. And so ultimately the threat should be disregarded. Now, of course, you could imagine other cases where, there's some kind of credible way of committing yourself to a strategy. Or, you can imagine that player 1 knows player 2 is irrational. But, in the absence of those other kinds of considerations, the threat's not a credible one.